Today we'll have one lecture because two for the first time it will be a little bit too much. You'll need some time to understand what are we doing, but you also get, every one of you will get a task, what you should do to next time by yourself in the modeling application. So today's lecture will look like this. First of all, I'll walk through the slides about the basic principles of VHDL. What is it? How does it work? And then I'll show you a little bit how to use the ModelSim software, and then you'll try modeling by yourself, each one as you like. So it will be a personal task. So you have do your personal tasks by your own. Yeah, and we'll discuss the results next time we meet. So I think it will be next time. Next time we shall meet next Wednesday, if I'm correct, if I'm right. Yeah.
Yes.
All right. So it's a little bit disappointing that we have only 5 students, but well, it's your choice. So skeleton of basics VHDL programming. So VHDL programming is a so-called hardware description language. Hardware description language, as I already told yesterday, it's some implementation of low-level programming. So usually we'll be able to view our source code as a circuit, as hardware. So we can imagine the program source code as a operating circuit, and we'll talk that there are 2 types of sentences of programming. There is the combinational and sequential logics. Combinational part is processed immediately, and the lag and the delay depends only on the parameters of logical components of which the circuit is built. If we are talking about sequential logic, in this case, the sequential circuits perform some tasks, including memories in a few cycles. So, for example, you need a memory cell to pass the value from one cycle to another when you start the next iteration. We'll talk about this logic later. The main difference between the FPGA and processor programming, that for processor programming, you have a program counter, and processor implements your commands one by one. So it works like this. You implement some command, then you shift your program counter by 1, and so on. You continue like that. In FPGA, we have no processor, we have no program counter, and also we had laboratory works using assembly, I think, for big microcontrollers, and you've learned that you have to shift some value into certain register. Then you can add something and read something from another part. Also, while you were doing laboratory works with interrupts, you were manually changing your program counter. You were jumping from a certain point to another point and then returning back. That's why you were saving some values which are in W register and so on. In this case, if we're talking about FPGA, it's an array built of logical elements. So usually it's or no 2 types of elements. Either there can be another architecture when we use and no 2 types of elements. You remember probably from logical programmable logic, you should have had some subject called, now it should be something like digital logics or something, or digital equipment or digital instruments. You should have some subject like that, and you probably know that using Carnot diagrams, you could simplify any view you have and transfer it into certain view built only of or and no elements. So that's the thing which is usually done by the synthesizer when you transfer your VHDL code into something you could upload to a port. as we're not able to work with board. So in this case, synthesizer passes it to simulator for simulation of a circuit. So VHDL program consists of collection of design units. There should be always 2 design units. Each design unit contains entity declaration and architecture body. There are 2 main parts which should consist in each design unit, in each program you code. So in this case, you can see that first of all we start with entity, and entity is the specification of your inputs and outputs. In other words, how your program is going to communicate with the outside world. The architecture body is part where you specify your code. What does your certain program does? So we could see that entity declaration. First of all, you start with entity name, and then port is declared the physical input and outputs of your program. So port name, port mode, and data type. How are you communicating with the outside world? And you finish the entity by also entity name. All right, let's see how does it look. Skeleton of basic VHDL program. The mode component can be, there are 3 different modes allowed for your port components for physical communication with the output. So it could be input, it could be output, or for communications it could be in-out for bidirectional ports. If you are, for example, trying to implement something like I2C or PS2, something like that. If you want to use some communication, then you'll probably have to use an input in-out type of your mode component. So for example, if we have entity named even detector, for some purposes we would like to build an even detector of once, for example, in our signal. So if it's an even detector, then the input should be some amount. It couldn't be 1 bit. So for example, in this case we'll talk about the signal type. This is the signal type as the STD logic vector. A little bit later today I'll explain what's the meaning of STD logic vector. So it's a 2 down to 0 array, so it's 3-bit array, and output is named even, and it's STD logic single bit output, as it's either it's even, either not. The main idea, what you should avoid, you can never assign the output, assign the value of output to something. You cannot read the value of output. You are allowed to read values of input only. So, for example, if we have some program like this, we are using some libraries. I also will talk a little bit later about the libraries. We have entity named mode demo, for example, mode demo, and it has A and B are inputs, STD logic, X and Y are output, also STD logic of 1 bit. And for example, you assign the architecture. Architecture must be assigned to the mode demo. So wrong architecture of mode demo is, and we begin. So first of all, we assign value that X is A not B. Pretty simple architecture, or A and B it could be here, and any logical operator. All right, and when you decide to assign the value of X to Y, in standard programming it would work, but you assign some value and then use the value already. But you have to know that X in this purpose is just an output signal. It's not a variable, and you cannot store anything in it. So your synthesizer will analyze the circuit like this, and it will directly connect X to the output to Y. So X, instead of calculating A and B value and transferring it to somewhere, it will connect two outputs together. So it won't work. Usually it can cause some hazard operations. So usually synthesizer will declare that you have an error in your design and won't compile and won't synthesize that design. In real life, what you should do, for example, you are allowed to use some intermediate signals, some additional signals. So in this case, we have AB is a redundant signal, which is not directly connected to any input or output. So first of all, we calculate the signal AB and then assign the values of AB to X and to Y separately. In this case, it will be a good practice, good program, and it will work properly. All right. Architecture body. The architecture body specifies the internal organization of a circuit. So mainly, if we talk about the other programming languages, for example, I'm pretty sure that most amount of you have pretty good knowledge in C programming. We could draw some parallel. That entity part is more likely, it looks like declaration of global variables in your programming, and architecture is the part of your part of programming. So architecture could have some declarations where you declare redundant or intermediate some signals which are local for that architecture inside it. So for example, AB is an internal signal of this architecture, and we declare it before the begin. After the begin, we have some concurrent statements. So it's concurrent logic or combinational logic. It's the part which is directly mapped into the circuit and the results are obtained immediately. So in all the answers of the concurrent statements are implemented at the same times in a single circuit, and the results are applied. The lag of the results depend only on the lag or delay time of logical component of which a certain concurrent logic statement is built. If we're talking about the sequential logic statements, in that case, it's like in the processor. Each statement is executed one by one. In concurrent logics, that's very important. It doesn't matter whether it's up or beneath. So above or beneath which statement goes first. They all are executed exactly at the same time as it's a concurrent logic. All right. So they are all executed in parallel. And the architecture, we have to also specify architecture name and assign it to certain entity. All right. The declaration part is optional and can include internal signal declarations or constant declarations. Also, if you don't need any signal or constants, you can avoid this part. All right, another design unit which could be used, package declaration. The packages is commonly is a collection of commonly used items such as data types, subprograms, and components. So you can load your components and subtypes from packages. So if we're gonna, in the laboratory works, we are using package to declare two-dimensional array, as it's not a variable type or a signal type, and we need to build it by ourselves. But maybe we'll cover it a little bit. Also, for the configuration, it's important that entity declaration can be assigned with multiple architectures. And for example, if you are working on several projects, but with the same entity. And in configuration, you just can assign which architecture you want to synthesize this time. Also, the HDL library is a place to store design units. So we'll need some special libraries. The basic library, which is always used, and it's the work library, where all the source codes are at. Also, we'll use some additional libraries. I'll discuss a little bit later about those libraries. All right. IEEE has developed several VHDL packages. So it's STD logic and numeric STD packages, the main packages we're going to use during our work. it's included by this. First of all, in the beginning of the source code, you write that we're going to use IEEE library, and we're going to import std logic 1164 for std logic operators. So yeah, the first lab invokes the library name, and later we have a subsequent library usage. All right, now the processing of VHDL code. It occurs in 3 stages. First stage is analysis. So as usual in any programming, first of all, it's a syntax check for syntax error. Second change is elaboration. This is routing and routing designs among themselves. And the last part is execution of a flattened design. All right, now the lexical elements of program format. Lexical elements, basic syntax units of VHDL programming include. You can have comments if you want to comment your source code. Identifiers. Identifiers are used to identify your process, to identify, in other words, to give a name to your entity, to give a name to your variable, to give a name to a signal. So any type of identifiers. For sure, system words, as in any other programming language. You have some special system words which are not allowed to use for variable or signal names, which are system reserved. Then again, numbers, characters, and also strings. All right. For comments. Comments are distinguished by adding 2 minuses in the beginning of the line. Now with the identifier. Identifier can only contain alphabetic letters, decimal digits, and underscore. So you cannot add minus or something like that. The first character must be a letter, and the last character cannot be an underscore. There also cannot be 2 subsequent underscores. It's also not allowed when naming your identifiers. So valid examples: A, 10, next state, memory address, enable, and so on. Invalid examples. We cannot use such symbols. Also, it cannot start with underscore. It cannot also start with number. It cannot end with underscore, and there could be no 2 subsequent underscores. Also, you should know that VHDL is completely insensitive, case insensitive. This means that it doesn't care at all whenever it's capital letter or not. So in eyes of VHDL, all these are exactly the same, but in a good source coding practice, what we're going to use, we're going to write the constant names using capital letters, and we'll try to use some identifiers for our signals and variables, maybe starting from capital or in capital letters, leaving all capitals, all caps only for constant. All right, now VHDL reserved words. Here you can see complete list of 1 or more reserved words. Well, it's just an example which words are not allowed to use for our identifiers, but it's as in all programming language. Each programming language you are employing for your purposes has its reserved system words. All right, then again, numbers can be written in several formats. Here we have integers. We can write it with the exponent and so on. Real numbers. Also, we could write numbers base 2 and so on. But what we're going to use, usually we're going to work with either with integers or with binary arrays. So it would be easier for you. All right. So the character. What is important to distinguish the writing of character and the string? If we have a character, a single one letter, it has single quotes. If we're talking about the string, we have more than one character, it's written in double quotes. This is very often it's a very often mistake in VHDL programming. Note for sure that the following are different. In this case, we have a 0, which is an integer. In this case, we have a single bit, which is 0. It's a binary value of a certain array. So we'll have to distinguish that. All right, VHDL is free format. This means that it doesn't care on line spacings you're using. So whatever you're using new line or you're not using new line, VHDL completely doesn't care. So it's not like in the Python where we have to separate lines properly and so on. Here you could write all the source code in a single line and it will still be synthesizable. But it is a very bad practice, especially for another person to read what you have done. So avoid that practice. All right. VHDL objects. Object is a name element that holds a value of specific data type. There are 4 kinds of objects we're going to use. So signal, variable, and constant are the main types. Also, there could be a file. You could import a file, but it's only for simulation. We're not going to work with that. So we are going to use signals and variables and constants. I think in 2 lectures we're going to talk about the differences between signals and variables, and you also will get a task for some modeling of signals and variables. You'll see that, and also alias, and it's a related construct to a signal or variable or constant, and it's very commonly used, and we're going to use a lot aliases. Alias is naming certain part of the signal. So you can, for example, have a 16 bits, so 2 bytes, word of 2 bytes, and certain part inside, 4 bits from the middle of that word, you could give it a name, certain name. All right, so signal declaration. So signal declaration starts like that. You write a word signal, then write signal name. There could be several subsequent signal names, then double dot and data type. Signal assignment is performed like that: arrow and equal, and this points also the direction of the assignment. In who are maybe had some practice in programming with using Delphi, they know that in that case you have to use double dot and equal. If we are talking about the C, it's a single equal to assign value and double equal to compare values. In this case, it's assignment to the signal name, to certain signal name, some value. So the arrow points out the direction of the assignment. And the signals are interpreted as wires, connecting certain. Yes.
So there is an arrow and like there is a less than and equal. So this is a comparison, or this is assigning values?
No, it's assignment. It's written. It's signal assignment. So you assign certain value to a signal name. It's assignment.
So how will we compare them? Like if we need less than or equal a certain value and we need to compare 2 values?
We'll talk about it a little bit later today. Also, you'll see. It also depends on whenever in what part of the program it's implemented. But in this case, it's assigning. It's not comparing the signals. It's assigning of certain value to this signal name.
Thank you, Professor.
All right. So wires are signals are interpreted as wires. To ports in entity declaration are considered a signal. So this assignment is not something like you, for example, store some value in here. Signal doesn't have memory. It doesn't store any signals. It serves as a wire by delivering certain waveform through this wire to certain output, and that's all. It has no memory. If you change this part, it changes immediately, and that's all. Variable. Variable is some concept found from traditional programming languages, which represents a symbolic memory and location where value can be stored and modified. So if we're talking about the variables, we can also use variables in VHDL, and variables have no direct mapping to a hardware, and they can be declared only inside the processes. So variables, you can use variables only inside the processes, and variables already, when you declare a variable, synthesizer automatically maps certain amount of memory to store the variable value. That's the main difference. If variable is has dedicated memory, signal doesn't have any dedicated memory. And you have to understand that distinguishing VHDL and FPGA programming from traditional programming, that in this case so distinguishing VHDL programming to traditional programming, that usually signals are not memories, and they are completely different, and you can map it directly to a hardware. All right, so, and also you have to understand that in a FPGA you don't have registers, and as you don't have any registers, don't have any processors, you can build all the registers by yourself. For example, if you declare certain variable in traditional programming, for example, if we're using short int, it's 8-bit variable, and at the same time 8 bits in memory are immediately dedicated for that variable. But you cannot, for example, create a variable of 7 bits and so on. So if we're talking about the FPGA, we can build any type of register and store any length we like. It could be 3-bit, it could be 25-bit, anything we like. All right, let's continue. But we have to build all it by yourself, knowing what you're going to do. Variable declaration. So you write inside the process name variable system word, then variable name. It could be several subsequent variable names of the same data type. Variable assignment is executed the same type like in Delphi, 2 dots and equal. Contains no timing information. It's so-called immediate assignment of value name. We're going to use this assignment when we're going to work with constants, as we will assign certain initial value to a constant by immediate assignment. Both signals and variables can be assigned with initial values. Although useful in simulation, synthesis cannot deal with them for sure. Initial values are necessary only for simulation, and we'll talk about it, that when you transfer a value to the board, usually there is no initial values, especially if we're talking about the signals. All right. Now, constant is the constant value certain part. Also, you know that constant is very good for parameterizing of certain program. So we could have some constants on which all the parameters of a subsequent program depends. Right, so constant is declared the same way: system word constant, then constant name, data type, and then we necessarily have to assign certain value to that constant. For example, bus width is 32 bits, so this means that a bus width in bytes will be 32 divided by 8. That's pretty. It's also good to avoid hard literals, so-called to avoid hard coding. Yeah, so if we're going to calculate certain odd, for example, is the signal odd or even, and it should always depend on the bus width. So we can hard coding for cycle from I in 2 down to 0 is usually a bad idea, because this number should depend on the bus width. It's always better to use certain constant in the beginning of a program and then add it to the source code. In this case, you only have to change the bus width in the beginning, and will automatically change the other parts of a program. But it's pretty standard, good programming practice, so you all know what I'm talking about. Alias is not an object, but rather an alternative name for an object used to enhance reliability. So if you want to enhance readability, in other words, if you want for other people to make it easier to read what you have written in your source code, it's a very good idea to use aliases, and we're definitely going to use aliases. It's easy and nice to do. So for example, we have a signal word which is std logic vector 15 down to 0. So if we're talking about 15 down to 0, it's 2 bytes or 16 bits. We'll talk about vectors a little bit later. You'll understand. And we can assign names to certain parts of that system word. For example, we have OP std logic vector alias of 7 bits, 6 down to 0, and we assign this name to the bits 15th to 9th, the 7 highest bits with the name OP, and we can directly access them through that name. So we could name several parts of that register. That's a good way of understanding. All right. We'll consider the data types and operators in each library. So we're going to talk now about the 3 main libraries which we're going to use in VHDL. First one, which has no need to declare, it's automatically declared, it's standard VHDL library. Also, we're going to talk about the IEEE standard logic package and IEEE numeric package. And we'll also discuss what types does it bring and does it provide us with. All right. What is data type? Data type is defined as set of values and that an object can assume, a set of operations that can be performed on objects of this data type. So again, if we're talking about the traditional programming, if we have a char, such variable as char, it also is 8-bit or single byte character. Character could be single byte, could be 2 bytes. If we're talking about the Unicode, it would be 4 bytes. But let's talk about its simple ASCII character of 1 byte. So in other ways, it has 8 bits, and it can have value in decimal from 0 to 255. But the character number 64, for example, will be letter A, and 64 is at letter, but doesn't matter. 120 will be letter 8. So it has it's interpreted, it has a structure, and in register it's saved as a sequence of zeros and ones, but it's read as a letter, and you cannot add another letter to another. It has no mathematical functions. You can read it, add them to arrays, and so on. But you can use some compound functions, but you're not allowed to use mathematical implementation. If we're talking about the same 8-bit short int, it's just an integer. But if it's signed, the top bit will be corresponding to the sign. So it can have values from -27 to +127. So from -127 to +127, and that's all. And you can do some mathematical operations. But if the same short int is unsigned, it can have only positive values. So in this case, the same it can have values from 0 to 125, and the same number will have completely different value in this case. So that's the idea why do we need separate types, because in memory always each variable, each signal, it's just a sequence of ones and zeros in binary, but difference the values which could be stored, and difference the operations that can be performed with that certain variable. All right, let's continue. What we have to know about VHDL is a strongly typed language. So this means that an object can be assigned with the value of its type, and only the operations defined with a data type can be performed in object. Also, what you have to understand that distinguishing VHDL from any high-level programming language, you are not allowed to declare variable anywhere in the program. Like, for example, in C or especially in Python or PHP, you can declare variable anywhere immediately, and immediately assign value. In VHDL, there is a very strict area where you're allowed to declare variables and signals, and another area where you are allowed to operate with that variables. And that's all. No other manipulations. Also, if we're talking about PHP, it converts automatically by knowing which variable you're going to assign to which. In VHDL, you have to write all the conversion by yourself. Nothing will work automatically. All right. Data types in standard VHDL library. There are more data types, but the main types which we're going to use are integer. So integer is corresponding to the variable time known in traditional programming as long int. So it's a 4-bit variable, 4-byte variable, and it can have value from -2 in 30th stage to 2 in 30th stage. All right, and it has two subtypes: natural and positive. Boolean types, it's easy. Two types are false and true, and then bit is 0 and 1, and bit vector is a one-dimensional array. All right, now we'll reconnect and continue. All right, because time has ended, so prepare to reconnect. Everyone is back. That's nice. All right, so then let's continue. All right, so what's important that Boolean type can have only two values. It's false or true, and bit can also have only two values, 0 and 1. And bit vector is a one-dimensional array of bits. It's also easy to understand. All right. Data types and operators. The bit type is not versatile enough to handle other hardware values, like high impedance or free state, and wide or structures shortening. So the main problem is for the tree state stages, which is very important for microcontroller programming. We're going to use some special operators, some special signal types from another libraries. I'll return to tree state logic later a little bit. So there are about 30 operators in VHDL, and for sure each operator can only operate with certain data types. That's also pretty sure. So the data types and operators. So for integer, we can perform exponentiation, absolute value, and we can do a negation for Boolean and bit vector. All right. Again, with an integer, it's multiplication, division, modulo, and remainder, and always the result will be an integer. Also, we can use an identifier for integer, so it's either positive or negative. Addition, also for integer, and subtraction, also for integer. Now, the concentration is so-called compound functions, and compound functions are performed with one-dimension array elements, not with the integers. And we're going to use a lot of compound functions, especially for building certain signal. It will have to work about that. Okay. Now, shift left, shift right, shift left arithmetic, shift right arithmetic, rotate right, rotate left. It's the operators for bit vector. So I think you did all these operators. You have used it programming in assembly microcontrollers. Now, comparison. Comparison could be done if it's in different program type place, but in here it's not assignment. In here is comparison. So we can compare any type, equal, not equal, more equal, less equal, more, or greater than, and greater than equal. All right, and logical operators can be performed only for Boolean and bit vector type. So A and B or B, so it's so-called bitwise operators. Now the order of execution. So the highest priority is of exponential, absolute, and negation. Then we have all the multiplication, division, then arithmetics. So first of all, identification, then arithmetics of add, subtract, and compound functions. Then all compound functions, and the last ones are logical operators, which are executed bitwise. All right. Now, what for do we need std logic package? When we are using this library from this package, it introduces only two data types. The two types of signals or variables we're going to use, and the new data types are std logic and std logic vector. So it's easy to understand that std logic is a certain bit, and std logic vector is a string of in other words, one-dimensional array of these bits. So the importance that std logic consists of 9 possible values. It's 0 and 1, 2 values. Then high impedance state as a 3-state buffer, weak logic 0 and weak logic 1. For modeling again, or it could be, for example, for different voltages to distinguish these ones. Then again, unknown and weak unknown. And what's important for modeling, uninitialized value for simulation only when no value has been assigned yet. And also it could be don't care. So basically in the real world we use three states: 0, 1, and Z, the high impedance state. So what's the high? How do you understand the high impedance state? This means that we have certain high resistance on the output of our pin. If we're talking about a microcontroller or FPGA pin directly connected to the circuit. So if 0 or 1 is an output, it's employed to manipulate circuits somehow, to change the parameters of a circuit, to perform certain work. And if we're talking about Z, this means that we don't want to change any parameters. The input is a very high, it's an input, and it has a very high impedance. This means that it can read the parameters of a circuit, but doesn't change it at all. So for example, if we're talking about a field MOSFETs, field effect transistors of an output, which are mostly employed. So usually we'll have drain of a field effect transistor connected to an output directly. And if we are talking about the input, and for bipolar transistors, it will be the base. Yeah. All right. And for field effect transistors, it will be the gate connected directly to the pin. So if you remember the theory of MOSFETs, the gate is completely insulated from other parts. This means that it has an input impedance of several mega ohms. So this means it will get the high impedance state. So we reconnect instead of connecting the drain to connecting the gate. All right. Standard logic vector is an array of elements with STD logic data type. So, for example, if we want to declare signal, it will be signal name, and the type will be STD logic vector, and we specify the length of that signal. So 7 down to 0, the highest bit is number 7, the lowest is 0, so it's 8-bit signal. The most significant is labeled 7, as in any communications. So what's important, you can refer any single bit of a signal as you like. So, for example, we could address directly the first bit or the 5 highest bits if we need for certain purposes. All right, now operators for STD logic. So overloading of operators. This means that the same operators can operate not only with the data types they're designed for, but also with certain other data types. So the logical operators are overloaded for STD logic package. So we can use NOT operator, AND, OR, XOR, NAND, NOR. So all the bitwise operators can also operate with STD logic vector. Also, for sure, numeric operators cannot operate with this. This means that STD logic vector is interpreted not as a number, but as a STD logic bit array, and that's all. So only compound and bitwise operators can work, but none of arithmetic can work. Also, additional new operators should be included, as VHDL has a very strict rules for operating only with signals and variables of the same type. This means it has to introduce certain conversion. So 2-bit to STD logic, 2-bit vector, and to STD logic vector. Conversion from bit to STD logic. It's also pretty easy to understand. All right, so if we have signals S1, S2, S3 of STD logic vector of 8 bits, and signals B1 and B2 for bit vector, so the following statements are wrong because of the data mismatch. So we cannot assign directly bit vector to STD logic vector. We also can't perform AND operation between 2 STD logic vectors, but the answer will also be STD logic vector, and we cannot assign STD logic vector to bit vector. Also, we cannot operate with to perform OR between bit vector and STD logic vector. In this case, we need to perform certain conversion. So in this case, we just convert to STD logic vector, and there is no problem. In this case, again, we calculate logical AND, and then convert to bit vector. Here, we first of all convert to bit vector, and then have an answer. Also, we could write another way. We could convert to bit vector first of all, and later convert back to STD logic vector. Also pretty easy. Several operators are defined over one-dimensional array data type, including concentration, relational, and array aggregate. 3 types of operators for one-dimensional array. For relational operators, it's important that they have to be the same time of element, but the length may differ. So the shorter is element, the lower. If the higher bits are the same, but the lower bit is different, or one is longer and another is not, it depends on the length of an array. We'll see it like this. In this case, both elements are equal. That's true. In this case, it's compared bit by bit. 0 equal to 0, 1 equal to 1. 1 is more than 0. It's correct. In this case, 0, 0, 1. Oh, it's more. That's correct. And here we have 1, 1. It's equal. and there is nothing, and here we have 0. Oh, this means this one is more. And be careful with this. If we are talking about equal, if the length will differ, it will always be wrong. Okay. Concentration, or in traditional programming, so-called compound operators. Also very, very useful to shift elements inside. So when you're going to talk about the shift registers and going to build the shift registers and memory cells by ourselves, so it will be very important to operate properly with the compound operators. So for example, we concentrate 0, 0, 0, so it's a 2-bit array with a 6-bit array of A into a new variable of 8 bits. We also can concentrate free values, and we can take those free values with the same A. So we have 3 same values and then another part of the same array. We could also get the lower part of A and transfer it to a front. So in this case, we'd perform something called rotate right, like this. So assigning values to array aggregate. So you can assign value directly to array by just enumerating the whole array. We can assign positionally. 7th element of array is 1, 0, 0, and so on. We can perform name association. So 7th and 5th is 1 and other is 0s. We also can perform named association, just assigning 7 and 5 to 1 and all the others which are, and we don't know the amount of others, to 0. It's also assign all the ones which are left and assign them all with a certain single value. Note that assignment in this case is in opposite way. So the arrow goes to different stages when assigning certain value. All right, we can replace the first assignment with the second and not be concerned about the changes of the length. So if we know exactly the length of a signal or variable, we can assign it, or we can just write others equal to 0, and it will not depend. It will completely be independent on the length of array. It will assign it fully with zeros. So it will fill certain array with zeros. All right. Another library, IEEE numeric standard library, standard package, which includes 2 additional types. And now we're going to talk why do we need certain types. For example, if we have some signal A, B, and sum, and they're integer, and we want to add A plus B, and we only, for example, operate with small numbers. For example, if we want in our program, we're never going to use big numbers. We're going to add 4 plus 2, for example. But integer has a fixed length. It's always 32 bits, in other words, 4 bytes, like a long int. And that's all. So even if we want to work with small numbers, it will be a huge adder in our structure of FPGA and will use a lot of space in it, even if we want to operate with small numbers. So often it's very unuseful. It's very bad practice to use to waste our space like this. For example, if we need only 8-bit adder to add 2 numbers, or 4-bit adder, if we are not going to work with such a huge numbers, what for do we need to waste our space for 32-bit adder? In this case, we can use 2 types which are introduced by the package, and numeric STD package, and it has signed and unsigned. What's important to understand that signed and unsigned elements are built also of STD logic bits. So the bit is the same. It's also STD logic, but it's interpreted not as bit array, but we already read it as we already read it as a number. But usually the real outputs, if we're talking especially about arrays, we are used for communications. And for communications, it's very good idea to use compound functions and bit arrays. So usually the real outputs of our boards are std logic vector, and then they already later are casted into signed and unsigned. All right. So how does it work? We have library IEEE, use std logic, and use numeric std. So we have a signals x and y which are signed, and both are 2 bytes or 16 bits. And we can perform all the arithmetical functions. Now we're going to talk about the operators overloading. So the operators of the absolute, divide, mod, reminder, add, subtract can be overloaded for operation with signed and unsigned operators. Well, absolute value can be for sure calculated only for unsigned, for signed, as unsigned doesn't has, it's also of absolute value. So what can we do? If all the operators at the same time, A, B, C, D, are unsigned, we can add together. We can add integer to unsigned, as this integer number 1 is automatically converted into the same length unsigned or signed when we're adding them. So it's converted into B, into the type of B signal. So if B is 8 bits, synthesizer will convert 1 to 8-bit unsigned, and then we'll add them. All right. Relational operators also could be used as assigned and unsigned. Is indicated as a number. So in this case, if we are talking about a logic vector, it has one meaning for sure. It's right. But if we are talking about the unsigned, also, if we're talking about unsigned, this won't be right. But if we're talking about signed, once again, this one is free, and again -8. So you see, because the top bit is responsible for the sign. So it can have, in one case this one is free, in another case the same number is -8. All right. We'll talk about these types a little bit more. Then operator overloading and new functions. So we can have absolute value, arithmetic operations, relational operations, and some new functions which appear. First of all, shift left, shift right, rotate left, rotate right. First of all is the signal you want to rotate, and then another is a parameter. For example, shift left by some amount. All right, resize, compare, and now the most important, it's so-called data conversion. So we can convert A to integer, and integer convert to unsigned and to signed. Also, first of all, we write a number which we want to convert, for example, 5, and then we write a length of a signal we want to receive. So it will convert number 5 into certain length, signed or unsigned. Also, we have not only conversion, but so-called typecasting. Now I'm going to show you how does it look like. All right. It's the table when we're allowed to use conversion, and when we're when we are allowed to use so-called typecasting. So if the bits are different, so from integer to unsigned, we use the conversion with the word to unsigned to integer. So from unsigned to integer with no parameters, from integer to unsigned, we write the integer number we want to convert and also add the length of the unsigned, of the resulting unsigned. The same with the signed and with integer. In here, bit vectors are the same. This means that signed and unsigned consists of the same single bits, of same std logic type bits. So in this type, we don't write the word to, it's just casted std logic vector. So it's just not to, but just to std logic vector, and here it's signed. And again, it's casted from std logic vector to signed. The same with the unsigned. Right. Let's continue. All right. So typecasting and type conversion. So how does it look in real life? Examples of typecasting. We have signals U1, U2, V1, V2, unsigned std logic vector. If we want to cast from std logic vector to unsigned, we just write unsigned and cast. If we want to cast otherwise, we cast to std logic vector directly. All right. Now type conversion. We have signals S1, 2, 3, 4 to 6 std logic vector, U1 to U7 unsigned and signed. So okay, in this case we add two unsigned numbers, both operands are unsigned, that's okay. In this case it's also okay, as one is automatically converts to unsigned and natural. Okay, here it's wrong. Type mismatch, we cannot assign signed value to unsigned directly. Once again, it's integer, it's unsigned, type mismatch. To fix, we convert. In this case, we cast from signed to unsigned, not convert. In this case, we convert to unsigned. Yeah, typecasting, type conversion functions. All right. Here, we are trying to add signed to unsigned and receive unsigned value. That's not going to work like that. We can, it's two solutions. First of all, convert signed to unsigned and then add, and then write back to unsigned. As if it's unsigned, it's probably all values should be unsigned. But be careful, you can get very wrong answer in this case. Maybe it's better to convert everything to signed. We can convert this one to signed, then add them, and then convert to unsigned the whole answer. Again, signed to unsigned, type mismatch. In this case, we're trying to assign the logic vector with unsigned type mismatch, and here also type mismatch. It's important to understand, as you could see from the table before I showed you in our screen, that you cannot directly assign integer value to the std logic vector. It has to be performed in two steps. First of all, you convert it to unsigned, and then only unsigned could be converted into std logic vector. Here we just convert to std logic vector from unsigned. Here you cannot add to std logic vectors, as std logic vectors don't perform any mathematical operations, are not operational with std logic vector. So in this case, we convert to we cast to unsigned, add, and then cast back to std logic vector. Here again to unsigned and cast back to std logic vector. All right, so that's for the theory. Questions? So please ask any questions about the topic where we're talking now. Easier for you to understand. All right, so now I'm going to show a simple example just to introduce you model sim to get a little bit familiar. Also, as I have told you in the explanation of second laboratory work, there is an explanation how to use the software, but still it will be easier if I'll show you just at least a little bit, just first steps, and then you'll have to work by yourselves and perform certain work in personal. All right. So that's the software, model sim software. It's for modeling. What's important to understand? What are we doing? If we want to model properly, we have two programs. One is the one we are testing. Another is so-called test bench testing programs. You probably learned this in electronic devices and basics of electronics, that you can analyze the transistor as an active 4-pole, as I think it's called like that, when you don't care what's inside, but you just read some parameters from the outside and measure the curves. In this case, it's the same. The test bench doesn't know what is inside the testing program. You just connect the inputs to the inputs of a testing program to the outputs of a test bench, and read the outputs of a test program to the inputs of the test bench. So this means that you just apply certain signals to the inputs and read the output. How does it work? So it's pretty easy to manipulate this way. All right. So we'll start from writing simple program. So any simple program begins with library declaration, as we'll use this rule that input and output is always either std logic or std logic vector, like in real life, to get as maximally close as we can to the FPGA. Because in real life FPGA, we have some such things as routing, and routing, there is some UCF file called for routing directly outputs of our subprograms directly to the board outputs. So we are going to use library IEEE, and we're going to use std logic 1164 all. Alright, so here's our library. Then we always have to describe entity. So our entity is our program name. So entity, well, program, for example. Entity program is, and when we specify the port. So this is the direct inputs and outputs. So for the beginning, what we're going to do, we're going to use to do simple or element. So we have 2 bits as an inputs, and we can calculate what is logical or performed between these operators. So we have A as input. So A, and the type is std logic. B is also std logic, and for example, Y is our output, also std logic. Note that in the HDL there is no semicolon after the last statement before the brackets. That's pretty hard to remember. And entity declaration always ends with and entity name. So in program. Now we can call it, for example, program 1. Now we have to specify the architecture. Architecture, and then each architecture must have its name. Architecture, for example, behavioral, of, and then we assign architecture to our entity of program 1 is And here we can have certain declaration of signals if we're going to use, but we don't have any signals. So when we write begin, and after the begin, it's the only function which we're going to perform is y is assigned to a or b. That's all. And end, and after end we run it into behavior. All right, that's all. That's all the program. You see now it has a question mark. So we press compile, and compile selected. All right, let's see some where are the mistakes? Let's see some errors. Moment is yes, for sure. IEEE. All right, compile of program was successful. Great. Now we're going to write test bench to test whenever it works. Okay. So in the test bench. Okay. Then we're going to use the same library. Now, if we're going to use test bench to a program, we have to name it as always. So it's also must have entity, but we'll call it test bench of our program 1. And test bench doesn't have physical inputs and outputs. So is and we leave it empty. And now we have architecture. We can call it however we like. We can call it the same, also behavioral, doesn't matter. It's also given name, whichever you choose. Behavioral of, and once again you have to assign this architecture to your entity. And this part is very important. Now in this case we have to add we have to somehow perform a connection between our test bench and the actual program. So in VHDL it's done like that. We add our program as a component to our architecture. So it's done like that. We write the component, system mode component, and then write the component name to know how to connect. The component name must correspond to this one, program 1. And then we write as always is, and now for that part we just copy the whole port assignment. It has to be completely the same. All right, and that's basically it. The important part that when we write end, we don't write end program 1, we write end component. That's the part we have to remember. All right, we have added component when we write the begin. Before begin. Also, if we want to connect to A, B, and Y signals, we must have our own signals in our test bench to perform that connection. We have to we must have something to connect to these ones. So these are somehow like our in real programming variables of one program, and we now must have variables of this one program. Only this is not variables, this is signals in this type, but still it's internal signals of test bench, and these ones are signals of our program which we are going to test. So we have to define them. So write system word signal A, B, and Y, and all signals are the same type std logic. Right, now begin. And now the last part we have to do is we must write so-called port map. Now we have the signals of program 1, we have the signals of our test bench. Now we have connect this A to this A, this B to this B, and this Y to this Y. So it's done by port map. First of all, you have to name the port mapping. You have to specify the marker. It can be anything you like. Duty 1, my assign, anything you like. So, well, all right, duty 1. So, duty 1 assignment. Right, and then you have to write what component I'm going to assign. So the component is program 1. And then we start with the port map. Okay. And now we assign A. A should be assigned to, also assignment to other side, to A. So internal, external, and the same with B. And this time it's not semicolon but comma separated. And of course, no comma after the last one. We have to provide certain values. We have to write something. So we have to write certain values in this case. So now we'll try to write something like process, like a process to assigning values one by one. All right. Let's and as we'll apply these values in sequence, we have to use a sequential logic. So we'll assign values one by one. So we are going to use sequential logic. We have to use process. You can name process as you wish. Before the word system.process, you can write the name of a process. So we're going to use something like input output generator. And then we write system.process. And then begin. For sure, we can use declarations, but we don't need any declarations in this process. So first of all, we assign A with certain value. A is equal. First, let's begin from the beginning. 0, 0. B is the same. Yes. So first of all, both zeros. Now to see the result, we have to add certain wait time. We can use special simulation statement. Wait for 50 nanoseconds, for example. All right, then 0, 1, 1, 0, and 1, 1. So all four possible values are separated by 50 nanoseconds. All right, what we're going to do next, we're going to use some special AND statement to distinguish the end of modeling. When we press run all, it will cause a failure and stop modeling. And in this part, we write just end of the process. Sorry. Process, and once again, end the whole program and the whole architecture. All right, let's try to see how does it look like. Compile selected. Somewhere is an error. Let's see. What's wrong? Oh, sorry. Compiling is successful. Now, if we want to simulate, to start the simulation, what we're going to do? First of all, we go to the library tab, select work. Let's see, one moment. All right, go to library and select our program 1 we just built, and press right click and simulate. Now we'll wait for a few minutes, for a few seconds. Here the view changes. Very well. So now we have certain objects and the wave, and we add objects in here. All right, and now we press run all. Moment. Stop simulation. Something wrong. Right, and here we go. Somewhere with the software, somewhere, so we have some problem. I will reopen it. And simulate. Also, once again, okay, now it works. All right. So if we'll start from the beginning, we have our 2 programs, one and another one. We go to library, work, and when we choose what we want to simulate, we simulate not the program, but we always simulate the test bench, which shows, which connects to a program and shows the results. So we press right button, right click, simulate. All right, now something changes in our screens. We choose wave. If wave is not displayed, we press view, and here we have to select wave. Here we have an object, our 3 signals, which are connected directly to our simulational program. We drag and drop them to our wave window, and then we have to press run all. It starts simulation, and you could read here that it was modeling until the end of modeling. So I caused, and by this line, end of modeling, I caused the severity failure, which caused in stopping of modeling. So the modeling was automatically stopped at that place which we desire to stop the modeling. All right, and now we can zoom it, and we see that first of all, 0, 0, and the answer of OR is 0. 0, 1 is 1. 1, 0 is 1. 1, 1 is 1. For example, if we want to change OR into AND element, so it's easy to do. We just go to project, or directly here, go to program, go to program, and change from here to, for example, AND. All right, save. In this place, we have question mark. We press compile selected, and in order to simulate the view, we have simulate and press restart the simulation. We restart the simulation, then press run all once again, and here we have in wave completely different results. 0, 0, it's 0, 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. That's all. And simulate and end simulation. All right. Questions?
I tried doing the same as you did, but I'm getting an error loading design.
So somewhere you probably made a mistake.
It compiled correctly everything, but it doesn't simulate. It says that I should go to the website and update my version, even though it's the newest one.
I think that usually certain problems are when you have a very long path. This software doesn't like long paths at all. It likes when the path is short, directly to C drive somewhere.
Okay, I'll check.
All right. This part. Now, your task, what you'll do by yourselves. So we add new file. We'll call it add, for example. And in this file, what you're going to do? In this file, you're going to use two libraries. With program add, and here's program add. And here we are going to work with ST logic vectors of identify. And all the vectors will be 8 bits. And the idea will be to arithmetically add those two. But to add, you'll have to convert, or in this case, cast to unsigned. And then cast back to.
Should it be down 2? But because it's now down RO.
Down 2 for sure, It has to be down 2, definitely. Something like that. Somewhere. Let's see. Yeah. Sure. If here is program add, here is program add. So here it also must be program add. That's definitely. All right. So I'll add these source codes to the Moodle today. So your task for your today work is to model this program by yourself. So that's all from the theoretical part for today. So prior to next meeting, every one of you should have modeled this one and everything should work fine. If you have any questions, just write me an email. Also, don't forget that each lecturer in the department has so-called duty hours. So we can write me an email and we could meet during the duty hours via Zoom and discuss it privately if you have any questions. So don't hesitate to use it. So,
sir, I sent you an email yesterday about a subject with a similar name, Programmable Microsystems.
Yes, I discussed already it with department, the head of the department. It's strange that I don't see you and you don't see the subject in your schedule. Is that the problem, yeah? As I remember.
Yes, yeah, I see the subject in my manual system, but I don't see it on the schedule at all. It has no lecture, and even when I check the subject itself.
Yes, I'm going to meet today with the head of the department, and we're going to discuss the problem. I think we'll solve it out somehow. Don't worry about that.
Okay, thank you. So I'll wait for the replied email.
All right, now I've got everything yesterday. It was, I think, in the evening somehow. All right, so that's all for today. I'll add and explain the task what you have to do to next time today to Moodle. So if you have any questions, just ask or write me an email and we'll discuss.
Professor, what are your working times?
I don't remember now in a schedule, but you just can write me an email and we'll arrange it any possible which fits me and you. That's not such a problem. Just write an email and we can agree and meet, because if no, I'm not just waiting for with active Zoom for someone to call me. We can shift with time and arrange the time which fits you. All right, so that's all for today, and so see you on Wednesday. Don't forget, you all have to be prepared up to that time. All right, so thank you for attention.